Hello, and welcome to our last application of integration, and that is going to be continuous money flows or continuous income streams. And the idea behind this is that some large corporations they receive money almost constantly, right? They do business 24/7. Big online retailers are receiving transactions every moment of the day, every second, every microsecond almost. And each though, even though each single transaction is discrete, right? That happens once and there it is. It is reasonable because there are so many of them and they're happening so frequently. It's a reasonable approximation to model their income stream as if it were continuous. And not just continuous, but typically always changing from moment to moment. So with that in mind, we make the following definition that a money flow function, f of t, is a function that gives a rate, not the amount, but the rate of income, usually in dollars per year or thousands of dollars, millions of dollars, whatever it is per year, the rate at any given time t. So that is a money flow function. So as a quick example, let's say that this money flow function was in fact constant so that we could get a little handle on it. Of course, it's not usually, right? The rate that income arrives, that it comes in, hence the name, is typically changing for in every second. It's a different rate, but if we were to make this example easy, let's imagine that the rate of income was $10 million a year for a large corporation. And let's say that that was constant. So that's the same rate at any time t. Then how much income would the corporation receive after 2 years, after 6 months, after 1 day? And so if this is a constant rate, well, then it's pretty easy to figure out. If you've got 10 million a year and you've got 2 years, right? Well, a little exercise in your units, right? The units would cancel out here and you would have millions and $20 million over 2 years. Same thing over 6 months. So that's half a year. Units cancel. 0.5 times 10, $5 million. And the same thing here for 1 day. Well, that's 165th of a year. And so those units would cancel. And if you did that calculation, you would end up by getting $27,397.26 approximately, but it's money, right? And so if it's money, we round to 2 decimal places. So the idea of a constant rate is fairly easy to deal with. And let's just make one observation here before we go and let that rate change. So if we graphed our constant rate, well, then it is a straight line, right? At $10 million, here is f of t. And each of these amounts, I made a little mistake. 2.5 years here where it's only 2 years above. Regardless, you get the same idea. So that's not 20 million, that is 25 million. This should be here, 25 million. So each of those amounts, though, represent area. Right? If the function here is constant, then the height is constant, and that height is 10 million. And the base of each of those, the base is the length of time. So for example, for 6 months, or for 1 day, or for, well, 2.5 years. So you are looking at here base times height, so you're looking at area under this constant curve. And if we let f of t change, if we let the rate of income change, it turns out that it still is area under the curve. And obviously we need another way of calculating it, and that way is, of course, the integral. So the total amount of income from a continuous money flow f of t from time t equals t1 to t equals t2 is the integral from t1 to t2 of f of t dt. And to see why this is true, let's take a look here when we have this situation when the rate of income, again, it is the rate, it's the rate, not the amount. The rate of income is a changing rate. So obviously what we're going to do is express this as we have in so many other cases as a Riemann sum. So if we take our interval from t1 to t2 and we divide it into n subintervals of equal length, then delta t, which is the base of one of these rectangles that I've drawn, the base is t2 minus t1 over n. In each interval, pick an evaluation point. So in the ith interval, I've called that ti star. An evaluation point meaning that we will pick f of ti star as the height. And so we're going to make the approximation that the money flow is constant over that tiny little interval. And if it is constant over that interval, well, we just saw what you do when it's constant. If you have a constant amount, well, you multiply by the length of time. And what's the length of time? It's delta t. So the amount of income on the ith subinterval is f of ti star, the rate times the time length, times delta t. And of course, what do you want to do? You want to add up all of the amounts in the n subintervals, and so you've got the sum from I equals 1 to n of f of ti star delta t, and obviously the last step is to let the number of intervals go to infinity. So if we do this, it is no longer an approximation, so the limit as n goes to infinity of the sum from I equals 1 to n of f of ti star delta t is the integral. So like so many of the applications that we have seen, it is expressible as the limit of a Riemann sum and therefore as a definite integral. So let us go ahead and do a little example. Let's assume that a company's income stream going forward is given this. Right, so this is its income at the rate of income at any time t given in thousands of dollars per year. And what we want to know is what will be their total income over the next 2 years. So over the next 2 years, that's from now, which is t1 is equal to 0, to 2 years from now. So t2 is equal to 2. So it is the integral from, t1 to t2 of f of t dt. And that is equal to the integral from 0 to 2 of, here is f of t dt. Right, simple u substitution or mini sub even for you will give you this as the antiderivative top minus bottom, and you'll get an answer of $10,100,700 in the 2-year time interval. Well, is it the same over every 2-year time interval? Well, no, the rate changes. So if we have from year 2 to year 4, well, then we get the integral from 2 to 4 of the same function dt. Same antiderivative, but now obviously different bounds, and we see that we've got a different amount, 10,304,700, not 100,000, right? So this total income, this rate is variable, which is sort of the flexibility of using a function to describe the income rate, However, this model ignores interest. Obviously, if you get money coming in, you're not going to just let it sit there. Right? The mattress method is not a valid investment method. We're not going to shove this under our mattress and let it sit there. As soon as money comes in, you want to invest it to earn some interest. And so if you do, what can we do to the model? How can we adapt the model to take that interest into account? And so if we look here at continuous compounding and ask, well, what is the present value of a given money flow? A given money flow, remember, is from t1 to t2 of the income stream f of t dt. Well, if we're talking about a present value, then we always want to start this at 0. And typically we, in these problems, say until a time t years. So from here, when we talk present value, we're talking about from 0 to some later time t, to some later time t. And if we use continuous compounding, which we have seen a couple times now, so a is pert, right? A equals p to the e to the rt. A is the amount. Yes, this is the amount. P is the principal, which is the amount at time equals 0. So another way of saying this is that the P is the present value of the amount. So if we solve for P, that's like multiplying by e to the minus rt on both sides, and you will get this. P is a e to the minus rt. So if we let the amount be this f of t, right, those are the amounts that are coming in. The present value is f of t times e to the minus rt. So I said something a little imprecise there. F of t is a rate, not an amount, but we'll see how this makes sense in just a second. So how can we use this formula to represent the present value of a continuous income stream? Well, we're going to do, you guessed it, another Riemann sum. So we're going to divide our interval this time from 0 to t, into n equal subintervals. Each the length of delta t is t minus 0, or t over n. So in this case, we're going to make another little approximation. We're going to make the approximation, well, one, first of all, that the f is constant, that the f of t is constant on each subinterval, and that it comes in one single payment. So that we can multiply that payment by e to the rt, e to the minus rt, to get its present value. So if we do this, the money that flows in is approximately f of ti times delta t. Well, delta t is always the same, so I don't actually need that I. And it is received all at the same time, let's say, at ti. So we're using a right Riemann sum, and we're imagining a single payment in that time interval. And what do we do? Well, if each of those payments is to be present valued, we're going to multiply by e to the minus rt, where we've got this annual rate of r%. And each of those payments, right, at time ti, we're imagining that those come in a single payment, so we can multiply that single payment by this discounting factor, as it's called, right, to bring it back to the present value. And so we get the present value is, well, it's approximately this, right? And then obviously, right, what we want to do, we want to let the number of intervals go to infinity. And so you're taking the limit of your sum, and oh, wasn't that unexpected? An integral which is now not just the income stream, right? If we did the integral from 0 to t of f of t dt, that would be the total income. Which is not what we're after here. We're after the present value. And so if we multiply this by e to the minus rt, then we have exactly this present value formula of a continuous income stream. So let's look at another example here to demonstrate this. So a large corporation expects a rate of continuous income of $50 million a year over the next 4 years. And so f of t is 50 million, and it is a constant. It is a constant in this example. Assuming annual continuous interest rate of 7%, so r is 0.07. Find the present value of this income stream after the present value now from 4 years of continuous income. And so t is 4. So using our present value formula here, right, the integral from 0 to t of f of t e to the minus rt, here is our f of t, here is our e to the minus rt, from 0 to big T equals 4. That is just an integral that we know how to evaluate now. Simple little mini U sub. Here will give us this top minus bottom, and we get an answer of $174,440,184.67. Don't forget about those little change at the end. So a little bit more of a complicated example. Let's imagine now that here, so this is example 3, that our function, our rate of income is no longer constant. So our rate changes over the next 3 years. Find the present value of this income stream if the rate of continuous interest is 4.5%. Putting this all together, f of t is 2,500 times t. R is 0.045 and big T is 3 years. The same formula for present value, but now, oops, take a look at this. We have T times e to the minus 0.45t, which means that we are going to need integration by parts, IBP, to evaluate this. So the integral that comes out is not always just a simple u sub. You may have to do something a little bit more complicated. So here, if we take u as 2500t, then du is 2500 dt. If dv is e to the minus 0.045t, then v is, this is a little mini sub to get that back, and plugging this into the integration by parts formula, uv minus the integral of v du, but using this with bounds from 0 to 3, and you get the following. And then if you plug in those top minus bottom, right, and you just evaluate using the fundamental theorem, and you plug those in, you will find your answer now of $10,286.96. How come it's so little? That's the present value, right? That's the value now before any of this has income has arrived and been invested. So if we want the present value, a natural question will be, well, how do you find the future value? I'm so glad you asked, because I have a slide prepared just for that. So the future value of a continuous money flow is also known as the accumulated value. It's the value at the end. And so the value that would be accumulated over t years. So again, we're talking about from now to some end time, big T. And we are going to, again, base ourselves on A is equal to P e to the RT. This time now, A is going to be our future value. P is our present value, and we multiplying by e to the RT. Oh, but wait, hold your horses. Present value had a formula that we just derived, we just calculated. So if we plug in that present value here, we get that integral, and e to the RT, well, that just stays in place. And so there is our future value. There's our future value. It's the present value, e to the RT, times the present value formula that we just used. So another example here, using the future value of a money flow, the same money flow function over the next 3 years. So we got this present value. If we did this in 2 steps, we already had that answer from the last example. So we can just plug that in for the present value and multiply by e to the r big T, and doing that as a second step, right? This is a second step to example 3. Right, this is breaking the present value, no, the future value down into 2 steps. First step, present value. Second step, future value. But what if we wanted to do this all in one step? Well, what could we do? So let's look at the next example. A continuous money flow starts at $30,000 a year and grows exponentially at a rate of 3% per year. Find the accumulated amount of money, so future value, at the end of 6 years, so T is 6, if the money is worth 5% annual interest compounded continuously, so R is 0.05. Now, the little so-and-sos, they did not give us a formula for f of t this time, but they did tell us how to find it. since exponential growth is involved, we are using a pert again. Now this is, here A is 30,000 and P is, right, 30,000 is P e to the 0.3 times 0. So our principal amount is 30,000, right? That's what it's starting at, right? Which makes absolute sense. It says it starts at $30,000. So if we have these variables, then our function f of t becomes this. Now, I need to be careful here because this r, right, this was little r, whereas they gave us another rate here of the function. So that's big R, which is why we have two different values, right? This is big R, which is the rate that the rate that the income stream is growing at, whereas this R is the continuous compounding. So don't mix up the two, be careful. And then, so what do we have? We now have these values here, and so we are computing the present value using the present value formula exactly as we did before, but now here is our function f of t. Here is our discount factor e to the minus rt, and what do you know? Those two things can be combined. So the $30,000 is pulled outside of the integral. We are using a law of exponents in the numerator here, and then it is just a simple little mini substitution to get our answer. Now, you might notice, well, oh, no, not yet. I'm getting there. I'm getting ahead of myself. So we have this present value. If we want to find the future value, here is our second step. So after we found the present value, we multiply by the future value factor, which is e to the r times t. And so here it is, and there is our future value, present value, future value. Now, I had said doing it all in one step, and yet this is still a second step. Well, if we wanted to do this all together in one direct step, this t, big T is a constant, right? This is a constant. Little t is my variable. And so if this is a constant, I could just bring it inside the integral. And if I do, then these again have like bases, which means that we can add the exponents, and our single formula here for the future value becomes this, where big T is the end of our interval from 0 to t, so that is a constant. Big T is a constant, little t is a variable. So if we were to do that again with example 5, but now in a single step using this future value formula, we could plug in all of those things together in a single step, combine all of the like bases, and we get our answer here, which is exactly the same.